make this transpose times the vector x minus the vector mu, where the vector mu is the vector that has mu1 and mu2. So basically what I've...
should be a -1.
Oh yes, thank you very much. Because the sigma squareds are at the bottom and I'm moving up. So I've gone kind of quickly over this calculation because if you do machine learning, you do these all the time. I advise you to at home go slowly over these steps and convince yourself that these steps are correct. This is the multivariate Gaussian distribution, the Gaussian distribution for more than one variables. And the important thing here is if variables are independent, if one variable is not affected by another variable, that is manifest in the zeros in the diagonals of the covariance matrix. Okay, so now we can introduce the concept of likelihood. Let's assume that we have observed 3 data points in the world, and now we're back to 1D, and these data points are maybe 3 observations, 1, 0.5, and 1.5. So you're measuring some physical quantity, and you observe those 3 values. And you believe that those 3 values are governed by a Gaussian distribution. And your task, and you know that the variance is 1. You have some, from whatever knowledge that you have strong reason to believe that the variance is 1. So your question is, what is the mean of those variables? So what is the theta? And we know how you would compute it. You would just average them, right? The sample average was our approximation of the expectation of the mean. Here what I'm going to try to, with this very simple example, introduce the concept of likelihood. We're going to assume that these points are independent, again, that these points are not interacting. Like, for example, if I'm cooking, I can't say that every action that I do is independent, because whether I put something in the oven, that depends on whether I actually put something inside that tray. Otherwise, I'm just putting an empty tray in the oven. So my activities when I cook depend on previous activities. So in that case, my data is not independent. Each time depends on the previous thing. And soon we'll see, for most models, we have to relax that. But if all I have is realizations of images, I see an image and then I see another image and there's no connection between these images, those images are independent and I treat them as independent data. So a lot of the data that we will encounter, we will be able to treat as independent. And so independence in terms of probability just means that if I have 3 random variables describing my observations, or I have a random variable and I have 3 realizations of that, I can decompose that as, there should be a 2 there, as the product of those distributions. So independence means that P of A and B is P of A times P of B. And so now let's assume that I tell you there are 2 possible values that theta could have, 2.5 or 1. And then the question is, which one do you think it's more likely to be? Which theta do you think is more likely to be the one that generated the data? Any guesses?
1.
Yeah, if you just hide the data, 1 seems to be more obvious. The formal way to do this is, if you guess that theta is 1, okay, that's your guess, you would plot a Gaussian that has mean 1 and variance 1. And if you believe that the mean is 2.5, you would plot a Gaussian that has mean 2.5 and variance 1. And then what you would do to evaluate these probabilities is you would look at the height of each of the observations being 0.5, 1, and 1.5. And then what we do is we multiply those 3 heights, and the one that gives us the highest product is the one that's the most probable. That's the likelihood. That's essentially maximum likelihood. Each observation is treated as independent. We take their product And if the product is the highest, that's the one that's most likely, that's the one that we accept. And for this problem, this seems to be an overkill, because we could have just averaged and that would be enough. But then we'll see that the same principle can be used for any of the models I described in the introduction, whether it's a recurrent neural network or a differential Turing machine and so on. We're going to use this same principle to be able to figure out which parameterizations give better explanations of the data, regardless of what the data is, whether it's code or images or text. Okay, so if you're Gaussian distributed with mean, so the first thing is if you have a Gaussian, you can just essentially this gives you a noise model of, about the mean. So if you have a random variable that has got this value, you can describe it in terms of a height plus an oscillation signal. So a height which is this height and then some oscillation. So I can take this outside of the n. And so basically what we've now what we've been saying is that the y's are distributed according to a Gaussian distribution. Okay? So now we're going to look at regression, and we're going to allow for x's as well. So now we have a process that takes x as input and creates a y as output. The uncertainties in the y's, the probabilities of our y. X is given. There's no uncertainty. In our model so far, what we will assume is that there's no uncertainty in the x's. Someone gives you x, and then your goal is to predict y. X is given to you. It's a known input. And the parameters, we're also going to condition. There's no probability in the parameters. The parameters are quantity whose value you try to estimate. We'll see later there's something called Bayesian stats, which takes a different view on this. But from the perspective that we're looking at now of maximum likelihood, we're going to describe the probability of a vector whenever you have now regression where you had this vector of y1 all the way up to yn observations, and you had a matrix. So we had this vector y, and we had this matrix x, which had x1 all the way up to x1d, and then all the way up to xnd, so that as we had in the previous class. Then to describe the distribution, we will consider the distribution of each individual point y, and I will soon draw a diagram illustrating exactly what we're doing. But if you do this, and if you write this distribution for each point, so we basically say the mean of the point is a line. It's the line x times theta. And the rest is kind of tedious math. If you have a product of functions, especially exponentials, that's e to the sum. And then a quadratic form, as we saw last week, can be written as the dot, can be vectorized and written as the dot product of y minus x theta. So this starts looking interesting. Let me write it a bit more cleanly here. Because what you realize is that the probability of data for some parameters this line, by the way, I said it in words, but let me emphasize, this line in my notation means given. Anything to the right of that line is given, so you see it. There's no uncertainty about it. The only uncertainty is about the variables that are to the left. So data here is the random variable, because the universe is giving us data by sampling from some distribution. That can always basically be written as 1 over some constant, which we typically call z. That's the standard notation for the normalizing constant. And it's the constant that ensures that things sum to 1, so that you have a probability distribution over the data. E to the minus loss of data and parameters. parameters. Okay, so if you take a loss, you negate it, exponentiate it, and then you divide everything to make sure that that you get an integral that sums over the data that sums to 1, you get a probability. And we will interchangeably go from loss to probability by doing this. If you have a quadratic loss like this, or the mean squared loss, the mean squared error, mean squared loss, quadratic loss, then if you exponentiate it, multiply by a constant, which in this case is 1 over 2 sigma squared, and divide it by the right constant, which in this case is this 2 pi sigma squared to the minus n over 2, then you get a probability distribution. And this will be true for other types of data. Now, let's go and revisit our example last week, which was how to fit a line to observations x and y. Okay, so last week we saw that, okay, so our model is a line. So we have, the setting is, we have the y variable here, we have the x variable, and we observed several points. Something like, say, this. Okay, and so what we did is our task was to fit a line to these points, and we did this by requiring that these springs come to a minimum energy point. So that was our way of minimizing loss. So, and in particular, each of these guys is a point. These are the y coordinates. These are the x coordinate. This is the y coordinate. And the prediction here is what I call yi hat. And yi hat is essentially theta 1 plus xi times theta 2 is the evaluation of the model. What we're doing with probabilities is we essentially are placing a Gaussian at each of these points.
How do I access my personal information? You can ask any organization for access to records held about you. A government agency is not allowed to charge you for access to your personal information. But a private sector organization may charge a reasonable fee. Generally, they should give you access within 30 days. You can also ask for your personal information to be corrected. If they will not give you access or correct your information, they must give you notice in writing telling you why. For more information about privacy, visit our website at
www.oaic.gov.au. So it's kind of critical for you to pay attention to what's documented in your medical record.
Healthcare is a great field to get into. Health information technology is a really important part of any healthcare organization. We are preparing students to go out and manage all aspects of health data, electronically and paper format. Class sizes vary between 15 and 22 students, so it's a good size in order to give them the attention that they need to succeed in the course.
We are definitely working with an individual's health information. We are protecting that data, we are codifying that data, we are monitoring that data for for completion. Our world used to be very paper-based, and now our world is very electronic. We are working almost solely in a computerized environment. We are using software that is used in facilities. We are not using simulated software in most instances. We are using what these students will find when they get a job in the workforce. Our philosophy of teaching in the technical college system is different in that we want a lot more hands-on learning. We are really good at what we do. We have a passion for this profession.